Hello, AP Stat students. Today we're going to discuss independence and how it relates to probability. Remember, independent events means that we have events that do not affect one another. Okay, so if A and B are independent events, we have this definition right here. Oh, just move my whole screen. We have this definition right here, which says the probability of A will be equal to the probability of A given that B has already happened, which will also equal the probability of A given that B did not happen. Okay. So what this means is the probability of event A does not change if event B happens or does not happen, meaning that A does not depend on event B. So when this is true, we say A and B are independent. Okay. If event B happening does not change the probability that event A happened, then A and B are independent. Okay. Another result of this formula, or another formula we have for independence, is that if two events, A and B, are independent, so we know they're independent, then A intersect B will equal the probability of A times the probability of B. Remember, another way to say intersect is to say and. So the probability of A and B equals the probability of A times the probability of B. And that's only true if A and B are independent. Okay? So we have two formulas. The top formula is a great way to test if two things are independent. And the bottom formula is a way for us to find the probability of two independent events happening at the same time. We just multiply them together and we get the intersection. Moving to the Venn diagram picture, if you have mutually exclusive events where the two circles do not overlap, then there is no overlap, of course. So events A and B are then automatically dependent. Okay. So if this is your Venn diagram where there is no overlap between the two events, they are automatically independent 100% of the time. Okay, they can't be any other way. So mutually exclusive events are always dependent. And the reason is, if event B happens, then A can't happen. And if event A happens, then B can't happen. So the occurrence of one is affecting whether the other one can occur. And that is at the heart of what it means to be dependent. Two events that are affecting one another. In the bottom Venn diagram, where the two events overlap, these events can be independent or dependent, okay, depending on the situation and the numbers. So what we could do is we could use that formula and see if I multiply A times B, do I get the middle or the overlap? If I do, then the events are independent. If I multiply A times B and I do not get the overlap, then the events are automatically dependent. So when the two events overlap, you have to run a test to see if there's independence or not. It's not automatic one way or the other. Not like when the above picture, when they're mutually exclusive or disjoint, that's automatically dependent. So the result of that is we have two formulas. Formula number 5 is when we have two independent events. We can always find the overlap by multiplying the two events in question, A times B. And we also have then a test for independence, which is if the probability of A equals the probability of A given that B has happened. If that's a true statement, then events A and B are independent. Okay. And then, of course, you could use that formula 5 as a test for independence as well. If you know the probability of A and B and you know what the overlap was, you could test to see if you get the overlap when you make that product. And that's supposed to be an if it's true. All right, so let's do a couple. Now, here's an example of independence using a table. So to the right is a table representing your options for college roommates. So you could end up with people with a roommate who snores, which would be terrible, or a roommate who likes to party, okay? Or you could end up with someone who does both, which would be this 150 right here, or maybe someone who does neither, which is that 150 right there. So there's some different possibilities here. So question A says, find the probability you end up with a roommate who snores. Well, these are the snorers. Okay, so there are 350 people who snore. So the probability of snore is 350 out of the 1,000 people, which would be 35%. So 35% of everybody on this college campus snores. Now it says B, find the probability you end up with a roommate who snores given you get a roommate who likes to party. So it's probably a snore given you like to party. Well, we know from previous experience that if I'm given you like to party, then I know you're in this group right here. Okay, that you're in the 250 people in this group that like to party. Remember, the given goes on the bottom. And then I want to know what's the chance you snore if you're in that group. Well, that's 150 out of 250. So if we take 150 divided by 250, we end up with 60%. Okay, so then it says, are the events snoring and likes to party independent? Well, I can use our independence test, which said if the probability of A is the same, whether B happens or not, then events are independent. So we'll say, well, we'll check, is the probability of getting a roommate who snores, is it the same if I get a roommate who likes to party? Well, from above, I know there's a 35% chance we'll get someone who likes to snore, but there's a 60% chance of getting a person who snores if they like to party. So those are not true, they're not the same. So we'd say these events are dependent. Okay. Apparently, if you get someone who likes to party, it makes you more likely to find, to have that roommate be a snorer. Okay, so that's using that independence test. Okay, the fact that you like to party makes you more likely to be a snorer. Here's a Venn diagram example, and I don't know what events A and B are, and I don't really need to know. I know that the event A happening has a 50% chance, because I would add 30 and 20. I know the event B has a 30% chance of happening, because I'd add 20 and 10. I know that the chance of A and B happening is 20% based on, that's the overlap in the middle. So what do I know? A is 50%, B is 30%, okay? So let's take a look at the formulas. What's the probability that A happens? Well, that's the whole A circle, so that's 50%. And if I ask, what's the probability of A given B happens? Well, given B means I'm in the B circle, so I know for sure I'm in the B circle. The chance of that is 30%. And then I want to know what's the chance I'm in A and B. Well, that's the 20% in the middle. So that's 0.67 if you divide it. So the question is, are A and B independent? And we would say no. And my test is to compare those two values. And I found out that 50% does not equal 67. So A and B are dependent. Another way I could check this, could have checked this one. I'm going to change colors. I could have looked at A and B and see, is it the same as A times B? Well, A and B is 20%, and A times B is 50 times 30, which is 15%. Again, those are not equal, so that would mean that these events A and B are dependent. And that was using formula number 5. Now, another example says, suppose the gender of children is independent, and the probability of having a boy is 0.488%. Now, you might be saying, well, isn't it 50-50? But actually, there's a higher percentage chance of having a girl than a boy, just slightly. That's And there's biology reasons for that, because you need girls to keep the population going. You don't need as many guys, okay? So anyway, to have 4 boys in a row, and having boys is independent, then I can just multiply the chance of having each boy. So, first kid a boy, second kid a boy, third kid a boy, fourth kid a boy. So the chance the first one was a boy was 0.488, times the chance the second one was a boy, 0.488, etc. So what this is showing you is, if you have multiple independent events, all you have to do is multiply the probability of each event. So another way to do this would be to take 0.488 to the 4th power. And that is 0.0567. So just a little over a 6% chance, which is interesting to me, because that's exactly what happened in my family. I have 4 kids and they're all 4 boys. And there's only a 5% chance of that happening, which is 1 out of 20. So, basically if I got married 20 times and had families of 4, the chance of ending up with all 4 boys would only happen once out of those 20 times. So that's pretty crazy. Pretty unique family. Another question here: what is the probability Mr. Lang has at least 1 girl? So this is an interesting question. It's actually the chance, it's actually 1 minus the chance of them all being boys, which is 0.9433. So there was a 94% chance that I was going to have at least 1 girl in my family, and it just didn't happen. So we'll talk about this at least 1 girl option a little later on. Now the last one I want to show you is a tree diagram example of this. And for tree diagrams, it's pretty easy. So it says, draw a tree diagram showing independence. Well, independence means that one event does not affect the next. So let's say this was A, and this was a complement of A, and then this is B, B complement, B, B complement. Now, if A and B are independent, then it shouldn't matter if A happens or not. B should have the same chance of happening. So notice, whether A happens or not, the chance of B happening is always 60%. And the chance of B not happening is 40%, whether A happens or not. So these events are independent. Now, as opposed to this, let's say A happening was 30%, B happening was 7%. Now, if A happens, causes B to have an 80% chance of happening, and A not happening causes B to only have a 50% chance of happening or not happening, we say these events are dependent, okay? Because apparently A happening raises the chance that B happened, okay? After A happened, the chance of B happening was 80%. And after A didn't happen, the chance of B happening was only 50, okay? So notice if those second branches branch off and of equal probability, then the events are independent, like the first example. And if A happens and that changes the chance of B happening, then that's dependent.